Hi, welcome to DIY Electronics, of interest to anyone who enjoys electronics. I'm your host, Cody.
Today we're going to discuss resistors and their effects on circuits and how to determine the value of a resistor using the color code on fixed resistors. Resistors have a couple different schematic symbols that can be used. This right here is a fixed resistor. This is also a fixed resistor. Sometimes you'll see the potentiometers in a circuit which have a little arrow through and some other different schematic symbols that represent a resistor. But today I'm primarily going to focus on fixed resistors. Fixed resistors limit the current in a circuit, just as a water valve limits the amount of water that can come out. And if you were to barely turn the valve on, only a trickle would come out. If you were to turn it all the way open, then you got a gushing stream. It's the same with the resistor. The smaller the resistance, the less current the more current that flows, and the larger the resistance, the less current that will flow. Okay. So now let's actually look at some of these resistors that we got here. So now if we move on and look at the resistors, these right here I have in order from smallest wattage to the highest wattage. They're not in order from ohms, but the amount of watts that they can dissipate. This first resistor right here is a 1/8 watt resistor. The second resistor here is a 1/4 watt resistor. This one right here is a 1/2 watt, and this is a 1 watt resistor. Resistors are rated in wattages, and here are your standard resistors that you're going to use. 4 bands, and that's how the color code system is a 4-band system. If we move on down here and look at this resistor right here, this one is a 5-band resistor. If you see that it now has 5 bands instead of 4. This is a precision resistor. If we look at this resistor down here, it's another type of fixed resistor, but this one actually has the resistance labeled on it. And
so now I'm going to go ahead and explain how to actually calculate the value for a resistor using the color code. We have 2 types of resistors: the precision resistor, which is a 5-band, and a general purpose resistor, which is the 4-band. We're going to start off with the 4-band, and we're going to go ahead and use different colors than what are up here because this one's already solved. But let's just go with red, green, and then gold. Alright, so red would be 2, 2, and if you were to have a red band there and a red band here, so you'd follow that down, you'd say 2, and then go over here, follow that down, 2, and then our last band we said was going to be green, so we'll jump down here. That's 100K. So we'll take that 2, 2 and multiply it by 100,000. And that would give us 2.2 mega ohms, or 2.2 million. So that resistor, if it was 2, 2, or if it was red, green, gold, it would be 2.2 mega ohms, plus or minus 5% of the total ohms. Alright, now if we move down to our bottom resistor down here, let's just go with this resistor I have sitting on my desk, the one that I showed you in the video. It's red, yellow, black, red, gold, brown. So if we go to red, that's 2. If we go to yellow, that's 4. If we go to black, that's 0. And then we go to the multiplier, and it's red, so that's 100 ohms. So we have 2, 4, 0, 1, or 100. I'm sorry, because it's red. So we type in 240 times 100 equals 24K, plus or minus 1%. And that's why it's a precision resistor, because the values aren't going to be exactly what is labeled on the resistor. It's going to be plus or minus of that value. And it's always good to check your resistors with a multimeter before using them in a project, because resistors are made so cheaply, and depending on where you buy your resistors could depend on their quality assurance and everything else that goes along with it.
Okay, so now let's actually look at analyzing a circuit with resistors in it. I'm going to cover a couple different types of circuits. The first one we're going to look at is just a series circuit with one resistor. We have a 5-volt power supply and a 1K resistor. Only value we don't know is the current. So using Ohm's law, we know that current equals the voltage divided by the resistance. So the formula is going to be I equals V divided by R. We know both values, so let's plug them in. So it's going to be 5 volts divided by 1K equals, and then the handy dandy calculator. So 5 divided by 1000 equals 0.005, or 5 milliamps. So we know our current for the circuit's 5 milliamps. And that's pretty much all there is to the circuit. So we know anything after this has the possibility to draw 5 milliamps of current. And it can take away from that 5 milliamp and subtract, let's say 1 milliamp. So then the rest of the circuit only has 4 milliamps to work with. And that's the way that works. And that's a current limiting resistor. Okay, so now let's jump down here. This is a voltage divider. So first off, to get the current of the circuit, we first need to know the total resistance of the circuit. We have a 5-volt power supply and two 10K resistor and a 5K resistor. Whenever resistors are in series like this, you simply add them together. So our total resistance would be 10K plus 5K equals 15K. Bam. Alright, so now we know our total resistance. We'll just plug it into the formula and do it again. So it's 5 volts divided by 15K equals, punch that into our calculator. So we have -4, so that's going to be 4 zeros, 1, 2, 3, 3.3, and that's going to be 0.33 milliamps. So we don't even have quite 1 milliamp going through the circuit. You can also write that as 330 microamps. However you prefer it, I'm going with the 0.33 milliamps. So now that we know our amperage for the circuit is 0.33 milliamps, let's figure out what the voltage drop is across these. Oh yeah, by the way, the voltage drop on this one, since the circuit's set up like it is 5 volts, because Kirchhoff's law states that every point in the circuit must be equal, or everything must be equal out. I'll explain that in another video. But so the 5 volt voltage drop across that resistor. Okay. So now moving on here, what's our voltage drop across this 10K resistor? Well, now that we know our amperage, we can simply 10,000 times, and then I guess I'll just type it in. So our voltage drop across our 10K resistor is going to be 3.3 volts. And our voltage drop across our 5K resistor is going to be half that, so 1.65 volts. And because we rounded their milliamps, we're a little off, but we'll add them together, and plus 3.3, and we end up with a total voltage drop across these as 4.95 volts. And that's why rounding, you make sure that you get as far over as you can with your places. So our voltage drop across this, if we were to measure here and here, would be 3.3 volts roughly. And our voltage drop across here and here would be 1.65 volts. And this is a voltage divider. So using this circuit, you could tap out here and get your 3.3 volts from a 5 volt power supply using a 10K and 5K resistor. Now let's discuss finding values in parallel circuits. In parallel circuits, the voltage drop across each resistor is going to be the same as the power supply. So this resistor is going to drop 5 volts, that's going to drop 5 volts, and that's going to drop 5 volts. But the amperages across each resistor are going to be different. So let's go ahead and solve for the amperage of the first resistor there, 1K. So using our formula again, I equals V divided by R, so 5 volts divided by 1K equals 5 divided by 1,000, 5 milliamps. Alright, let's move on to our next leg. That's 5 volts divided by 2K equals 5 divided by 2,000 equals 2.5 milliamps. Let's look at the third leg there. That's 5 volts divided by 3,000 or 3K. So 5 divided by 3,000 equals 1.7 milliamps. Okay, now again with Kirchhoff's law, all these should add up to equal the total current in the circuit. Well, don't figure out the total current in the circuit, we first need to figure out total resistance. Unlike series circuits, you cannot simply add all the resistors. You have to use this equation up here. And you take the reciprocal of the resistors, and then you divide all of the reciprocals added by 1. So let's punch that in here. And this can get pretty messy. So you have to work with your parentheses. So it's going to be 1 divided by, open parentheses, open another parentheses for your first resistor, divided by 1,000. And then that's plus, open parentheses, 1 divided by 2,000, close parentheses, plus, open parentheses, 1 divided by 3,000, close parentheses, close the beginning parentheses, and divide. So our total ohms, or resistance total for this circuit, is going to be 545 ohms. So the RT equals 545 ohms. Wow. Okay, so now we can figure out what the total current in the circuit is going to be, a relevant total current. So 5 volts divided by our 545 ohms. So 5 divided by 545 equals 9.1 milliamps. So let's take what we got here and add them up. So we said our total current in the circuit is going to be 9.1 milliamps. We know we got 5 milliamps across R1, 2.5 milliamps across R2, and 1.7 milliamps across R3. So 5 milliamps plus 2.5 milliamps plus 1.7 milliamps equals 9.2 milliamps. And the reason that is because of rounding. I should have left that one at 1.6 and that wouldn't have jumped up. But there we go. That's parallel circuits.